All right, I think it's going.
Okay, good day, good day, depending where you are. Welcome to this first seminar, very distinguished seminar of the new Stochastic Programming Seminars virtual series that starts today and will continue with fortnightly frequency. At regular times, it is actually 10 a.m. Eastern time. So today, because of previous seminars at Stan's place, we start at this time. So it is a great pleasure to introduce Stan Uryasev, who will be presenting today further developments on this quadrangle theory that developed over, say, the last 10 to 15 years in collaboration with Terry Rockefeller. Stan is currently professor at Stony Brook, professor of quantitative finance, where he also manages regularly a very distinguished series of webinars that I encourage those interested in finance to follow. And he was previously at University of Florida. He has quite a remarkable record of contributions, and his editor, chief editor of the Journal of Risk, where he actually published in 2000 this fundamental contribution on conditional value at risk optimization, which has been, become a standard. It is among the most cited articles, I would say worldwide in our field. So something that he didn't write in his bio, but I would like to mention is that Stan had his PhD in early times under the supervision of Professor Moriev, so who is one of the founders of stochastic programming. So it is a very big pleasure to have you here today, Stan, for this first seminar. So I leave you the word, and you have 45 minutes, as I was mentioning, and then we may take some questions. So he will be presenting, an extension of his quadrangle theory with applications to statistics and data mining and portfolio optimization, joint work with Anton Malandi and Cheng Peng. Thanks a lot, Stan.
Georgi, thanks a lot for the nice introduction. I will be discussing today some recent results related to risk quadrangle. These ideas were already suggested quite a number of years ago, like 15 years ago, but only relatively recently quadrangle theory led us to a lot of new, quite interesting results interpreting various operations research and statistical techniques such as support vector regression and others. So let's I proceed. Here is outline of the presentation. Probably I will not go through this outline. Since there are also some practitioners participating in this webinar, I want to mention that all my students are funded by so-called spur internship projects supported by industry, and roughly speaking is something like company pays some check to the university, and the student is working 50% time for the company and 50% time doing the research. So my PhD students, Anton Malandi and Cheng Peng, who are major contributors to this presentation, funded by such spare grants from industry. And I'm just mentioning that if some industry participants want to fund PhD or master students here, then you're welcome to contact me. So I'm using this opportunities as advertisement of such type of possibilities. So what the risk quadrangle is about? It turned out that risk functionals, some stochastic functionals, can be united in groups or subgroups, which we'll call quadrangles. And it's called quadrangle because there are 4 corners in the quadrangle for stochastic functionals. And these functionals are error, regret, deviation, and risk. I would say that like error and regret and like a mother and father, and the kids deviation and risk, because through some formulas you can obtain from error deviation and from regret risk. And but regret and risk is almost the same stuff, they just differ by expectation. And risk and deviation almost the same functions that differ by expectation. And along the way, when we are trying to get from error deviation, we are obtaining a so-called statistic. And this statistic plays a major role in statistical estimation theory, which we will be discussing further. So what's the meaning of error? It's something like, say, mean squared error, mean absolute error. Regret is, I don't have a clear explanation what is a regret is. And sorry, this is error, this is a regret. Deviation is some measure of non-constancy, like a standard deviation. And risk is measuring level of losses, like maximum loss or expected loss. And statistic is associated with some formulas which we are running to get deviation and risk. So what are the formulas which are linking error and deviation and regret and risk? If you have an error depending upon the random variable, and then you take a constant c here, which is now a variable c, if you minimize with respect to c, you get a deviation, okay? And similar formula is for risk. If you have a regret random value minus c plus c minimized with respect to c, you get a risk. And then there are relationships which are linking risk and deviation. Risk equals deviation plus expected value, and error plus expected value equals regret. And pay attention now, when you do this minimization, then there is an arg minimum C, and this arg minimum C in both formulas is the same, and it's called statistic, okay? So far, it may be just formulas for you, but now I will explain shortly how you can use these formulas right away to build optimization or statistical estimation procedures, okay? Here are some definitions, and Q alpha is value at risk in finance, or it's actually inverse of CDF or quantile in mathematics, and Q bar is a conditional value at risk. For continuous distributions, actually, it's expected value in excess of quantile. That's why it's called conditional value at risk, because it's expected value in excess of value at risk. Alternatively, it can be calculated as an average of quantile. Now, let's give several ideas how quadrangle is defined. Quadrangle elements is defined axiomatically. So risk, which quantifies the risk, has the following axiom. So main axiom is risk of constant equals constant, convexity, closeness. There are various variants of definitions of axiomatic definitions for risk, but we have these axiomatic setting, and adversity, it means that risks strictly exceeds expected value. And similar axioms are for other elements, okay? For instance, deviation has almost the same axioms as risk, but risk of constant equals constant, but deviation of constants equals 0. But here, aversity and positiveness are similar properties, okay? Now, probably the most famous quadrangle which we have started with is a quantile quadrangle. Quantile quadrangle, usually quadrangles are called by the name of statistic. And we know from just give me a minute, I will move this bar. We know from original paper which I have with Professor Rockefeller about conditional value at risk that if you have expected value of x minus c, positive part, 1 minus alpha c, minimize with respect to c, you get a conditional value at risk. And arg minimum here is quantile, okay? So, later I figure out that almost the same formula is valid when you work with a quantile regression. And again, arg minimum is quantile. So what the quantile regression is about? When you have the error, you have positive and negative part and weighted average with coefficient lambda, it's normalized concave Bassett error, then there is an error. And if you take this error, minimize with respect to c, you again get arg minimum will be quantile, and then later on it turned out that these procedures, when you take arg minimum of error, concurrent Bassett error, and arg minimum of regret expression, because here is the regret, leads to nearly the same procedures, but people never established the fact that quantile regression and optimization of regret formula leads to the same quantile. And now let's try to explain with you with examples how it's why it's important in general case, okay? First of all, let's discuss how we can use expression which is this expression when you minimize with respect to C regret expression and get a risk, okay? So suppose that you want to minimize the risk, okay? You minimize risk, and risk depends upon some loss function L, which depends upon some vector of decision variables. Say, for instance, loss is a linear loss, okay? Then since risk is presented through regret expression, then we can write risk of loss as a minimum with respect to C. And now you have double minimization, X and C. What you can write now that you minimize this expression simultaneously with respect to X and C. So it appears that minimization of risk can be reduced to minimization of regret with extra variable, okay? And frequently it turns out that minimization of regret is much easier than minimization of risk. And let's have a look, for instance, here at this formula. When you want to minimize, say, CVAR, then you can minimize expected value of loss exceeding C positive part. And as if L is linear, then this is a piecewise linear problem with respect to NC, and this turned out to be convex programming reduced to linear programming if you have fixed number of scenarios, and it's a very efficient formulation for minimizing risk. And then recently, what has been showed in a paper with Melandy, Kuzmenko, Uryasev, and originally by Kuzmenko, that if you have a so-called expectile, I will discuss later what the expectile is. If you have expectile risk, then there is a similar expression where you would express it through regret, and through this regret expression, we have a minimization formula. So we immediately have an approach for minimization of expectile risk through formulas similar to that, okay? Now, one more direct output from quadrangle theory related to statistics, because let's make the following definitions. Suppose you want to approximate y and x are regressors or factors, and let's we formulate residual as y minus function f of regressors factors and c, which is a residual, and I want to keep residual separately from this function which depends upon x, and so that's my residual, and this my residual without c. I will denote. Okay, now let's say that you want to minimize error of residual, and residual can be written as y minus f minus c, so I can write it this way. And now you see that error minus c, this is random value minus c, and we know that minimization of error with respect to c leads to deviation, and there is an optimal analytical solution which is the statistics for c, which immediately leads to a simple fact which is not known to statisticians, that in almost all statistical problems when you work, you don't need to minimize error. You can minimize deviation, okay? Because minimum with respect to c leads to deviation. So you can minimize deviation of residual without intercept, and then for intercepts there is an analytical solution. So it means that when you minimize mean squared error, instead of minimizing mean squared error, you can minimize standard deviation without intercept, and for intercept you have an analytical solution which will be equal to expected value of optimal residual without c. Okay. Now, this leads to the fact that if you have an error minimization problem, and under some conditions, actually it's known that minimization of error leads to estimation of something, that if you minimize mean squared error, then you estimate actually mean value. If you minimize a mean absolute error, then you estimate mean value, median. Now there is a general theorem which says that if you minimize error and there is a statistic S under certain conditions, that whatever you have minimized is actually conditional statistic, conditioning that you know the value of factors, okay? So this immediately leads to the fact that if you want to optimize, if you want to estimate some statistic like a mean value or quantile or whatever, you should find a quadrangle where S is a statistic and minimize appropriate error, okay? And that's why if you have these quadrangle, where error is concurrent Bassett error and statistic is quantile, you are estimating quantiles. You're estimating conditional quantiles, okay? Now, there are quite a number of errors and appropriate deviations. Say, for instance, mean squared error, least square, standard deviations, and is expectile regression. Then you can minimize appropriate deviation measure and take C as expectile, then median or quantile. So there are many different examples. So far, what I have discussed is quite well known, but now let's discuss some new results which are related to support vector regression. Support vector regression was and is a very popular topic because almost all students or assistant professors are supposed to write a paper if you are at a computer science department, and support vector regression is the most popular topic. They just run numerical examples and just present it, and that's a paper, okay? And it can be shown that support vector regression is based on so-called epsilon sensitive loss. You have an absolute value of residual minus epsilon positive part. It means that only if residual is bigger than epsilon, then you take into account this loss. And you take expected value of such type of loss and plus regularization, and you minimize this function, and that's regression. And definitely this Z in this case is a residual, and residual is the difference between one-year track and approximation. So nothing special here except quite sophisticated, unusual epsilon insensitive function. And nobody actually asked the question so far, what kind of what is estimated by this regression, okay? And we answered this question, and it turned out that this regression axiomatically estimates a mixture of two quantiles, okay? There is another variant of support vector regression, so-called new SVR. And this new SVR, I will not discuss in details, but actually it can be reduced to minimizing so-called CVAR norm. So CVAR norm is expected value of CVAR norm is a CVAR of absolute value of random value, okay? So and another variant turned out to be the minimizing of CVAR norm normalized. Now recently Anton Masfasalov, my PhD student, that was earlier result of my former PhD student, Mofasalov. He showed that if you have CVAR norm, then quadrangle is as follows, and statistic is a mixture of two quantiles. So quantile 1 minus alpha, 1 plus alpha divided by 2. And from that immediately follows, if you have as a statistical problem where you would minimize this norm, that you estimate mixture of these two quantiles, which people don't know about because they have no idea about this type of relationship. Okay. Now, the other variant which I have started with when you have a Vapnik error, then for this type of error, Anton Malandi recently got result that with this error, statistics actually is a union of weighted average of two quantiles. This S1 is a mixture of weighted mixture of two quantiles, the same quantiles as S1. So statistic is a union of this type of quantiles. And so this immediately says, what do we estimate with a support vector regression? We estimate mixture of quantiles. And now, since there is a degree of freedom in selecting the parameter, if you adjust the parameter x, we estimate different mixture of quantiles, and this mixture of quantiles could estimate mean value, a median, or whatever, depending upon what kind of parameter x you pick. Okay. Now, from these, since we know what do we estimate, and since statistics are the same in these two quadrangles, that we could immediately have equivalency theorems about these statistical procedures, that there is a epsilon SVR and nu SVR are equivalent. Also, since error minimization can be reduced to minimizing of deviation, we could minimize deviation corresponding to these errors rather than errors. And for instance, deviation for CVAR norm, it's a CVAR deviation. So it turned out that to minimize, to solve support vector regression, actually you can minimize CVAR, okay? And there are packages for CVAR minimization, so you could use immediately standard software packages for CVAR to solve this regression problem. These analytical expressions through stochastic functions give a possibility to formulate nice dual formulations. And in this area, support vector regression, people work with linear programming formulations that don't form compact presentations through stochastic functions. And these stochastic functions have advantages because we immediately know what the dual is and so on. Okay. And these dual formulations also allows for kernel representation. I'm kind of fast because I want really to provide you a quick impression about what kind of results are here, and then later I give you references. If of interest, you could look through relevant papers. So the outcome is that we are actually estimating weighted average of two quantiles with two different variants of support vector regression. Now let's come to another set of new results which are related to expectile optimization and estimation. What the expectile is? We know that if we take a mean squared error, positive squares and negative squares, and equally weight them, then it will be mean squared error. And arc minimum mean squared error will be expected value. But now let's look at the error where we non-equally weight squares of positive part residual and squares of negative part of residual. So arc minimum of this function, if you take x minus c, arc minimum with respect to c will be equal to expectile. So special cases expectation when q equals 1/2. Okay, and the most trivial quadrangle which immediately comes to your mind, it's if you take error here, and just by definition here is arg minimum is expectile, so expectile quadrangle, the most simple variant, is coming right away. Okay, but now Kuzmenko and further has been developed in our joint paper with Malandi, studied some other quadrangle, which is a piecewise linear quadrangle. And this quadrangle follows from the following fact that actually, when you look at the optimality condition for this expectile error, then it can be written as this type of equation. Okay, and therefore, if you write this value, maximum of this part and that part, arg minimum also will be equal to expectile. So this means that there is one more quadrangle where it's a piecewise linear function, and it's minus expectation x and maximum of expected positive part. And again, if you minimize with respect to C, then arg minimum also will be expectile. So there is an alternative statistical technique immediately, which allows for estimation of expectile when you would minimize these error rather than the previous error. Okay, and on top of it, what it happened in this quadrangle that if you take error minus expected value, will be piecewise linear regret, how it looks like. And through regret, you get risk, and turn out that risk also equals expectile. So now what it happens that if you, for instance, take regret expression and minimize regret expression, then you get a risk which is expectile, and arg minimum also is expectile because the statistic also expectile. This is an absolutely exciting results which show that say so significant risk measure as an expectile can be handled through convex programming, through linear programming versus quadratic programming, which is here. Okay. And on top of it, it's known, and there is another variant of this expression that actually, if you take a C-var deviation, it's a C-var x minus expected value, C-var deviation, and then supremum of C-var deviation actually equals to expectile deviation. Okay, and now since we have a relationship between these deviations, and we know that regression problems can be reduced to deviations, that immediately leads us to impression that since C-var deviation can be used to calculate expectile deviation, then that C-var related C-var related problems such as a concurrent Bassett minimization should actually be equivalent to expectile regression problem, because there is equivalence or relationship between deviations. Okay, and then it indeed turned out to be that since we have this formula relationship to different deviations, that if you minimize deviation in quantile quadrangle, which is C-var deviation, or we minimize deviation in expectile quadrangle, that they lead to the same solutions. And moreover, if we put a constraint on expected value, since deviation and risk differ by expectations, then minimization of expectile risk and C-var risk, the equivalent condition there is expectation constraint. And that's a really surprising problem. That's a really surprising result, because it looked like a minimization of CVAR and minimization of expectile. These are different problems, but they're just equivalent, okay? And this is possible by having all these relationships to discover these things, okay? Now, I mentioned to you about expectile optimization to begin with, and since we have regret expression for expectile regret, so expectile regret, if you take expectile regret, then you minimize with factor C plus C, minimum will be equal to expectile, okay? And that's just consequence of expectile quadrangle. Now we could minimize expectile through linear programming by picking up one more variable. So here now you see that this is the dream function for stochastic programmer, because it's a positive part of, say, if L is linear minus C is positive part of linear function, and then I got again a positive part, so it immediately reduced to convex. No, it's convex program to begin with respect to C and X, but it can be immediately reduced to linear programming if you have fixed number of scenarios, which provides an alternative way to minimize the expectile risk. Okay, and on top of it, as I already mentioned, that expectile portfolio optimization and CVAR portfolio optimization, these equivalent procedures. Okay. Moreover, actually, I was a consultant for one hedge fund which worked with so-called Amiga functions, which is I don't have time to get into this business. Amiga is expected overperformance divided by expected underperformance, and we have a paper with Wagner showing that Amiga maximization is equivalent to expectile minimization. And then since expectile minimization is equivalent to CVAR, then also Amiga portfolio optimization is equivalent to CVAR optimization. So the hedge fund actually hired me as a consultant to explain how to optimize this Amiga, because that's what they were interested in. But at that time, I didn't know that this is just equivalence to CVAR, and that all the portfolios which you can get through Amiga optimization can be obtained through CVAR optimization, and that's an equivalence theorem. Okay. And expectile estimation with linear regression, again, we have different error functions with the same statistic, and we actually show that regression with, say, asymmetric variance error, or with piecewise linear error, or normalized concrete Bassett error, so it's a quantile regression. They also are equivalent. Okay, how could it be? Whatever you take, everything is equivalent, definitely under certain conditions. Okay, but here are equivalence theorems of piecewise linear and asymmetric variance error, and different variants of equivalence theorems. And there is a relationships between arg minimums, because if you have convex functions that minimizer may not be unique. Okay, so now it's equivalence of concrete Bassett error and piecewise linear error which you have in expectile regression. Ultimately, if you take these three different regressions, there is a inclusive relationships between optimal solution of these regression problems, and concurrent Bassett minimization, quantile regression has biggest set. Okay, so here are just summary of about these equivalences, and most recent results, which have not been even published by Anton. There is one more quadrangle which is called bias mean quadrangle, and this bias mean quadrangle is based on super expectation error by Rockefeller and Royce with some slight twists. So if you take maximum expected value x minus negative part minus x, which is a parameter positive part, and here, so you have a such type of error, then statistic here is expected value plus x parameter. Now, if x is 0, then you're estimating mean value similar like when you're estimating mean squared error. But now you can estimate mean value using piecewise linear functions, which may be reduced to linear programming. First of all. Second, you can estimate expected value plus some bias. For instance, if you want to estimate what kind of parameters or factors are impacting hedge fund which has loss higher than current value by value x, or there is an expected release of radiation for nuclear reactor, and then the question if there is a release significantly higher than expected value, what kind of factors are driving this type of release, and turn out that you need to minimize this type of error. And for this bias mean quadrangle, there are some relevant results. Okay, and but what is even more strange turned out to be that there is equivalence between this super expectation and concurrent Bassett error regression. So quantile regression and this. So you can use a quantile regression to estimate this bias mean, including the standard mean. How could it be? Okay, and these are similar theorems about equivalence. And finally, my time is almost over. I want to mention one more quadrangle where there is a Rockefeller error, where mixed weighted average of concurrent Bassett error, which estimates mixed quantiles. Since we see that this mixture of quantiles is a statistics for support vector regression or something like that. The same statistic can be organized by minimizing concurrent Bassett, not Rockefeller error. So there are plenty of unbelievable relationships, and also I want to mention that there is a set of new results about 5 divergence quadrangle. And this 5 divergence quadrangle, we have a working paper about that. I will be providing you the reference because I don't have time to review with you 5 divergence quadrangle. And 5 divergence risk is defined as follows, and deviation and error, and this leads to very interesting duality results, which are showing, for instance, that Markovi's portfolio optimization is actually a robust variant of some stochastic optimization, and least square regression is a robust variant of minimization of deviation. And it turned out that these two optimization problems are intrinsically, deeply interrelated through the fact that they are coming from the same quadrangle, from the same 5 divergence quadrangle, okay? And there is a dual and primal variant 5 divergence quadrangle. And there are a lot of things which I want to share with you. But anyway, objective of my presentation was to draw some interest to this fascinating risk quadrangle theory, and I think many more fundamental results will be coming out of this concept, and I believe that the quadrangle paper, the first quadrangle paper which we had with Rockefeller, that's probably the most interesting and fundamental paper which we had together. And currently we are writing extension of this quadrangle paper, which will absorb most recent results which I have just shared with you. Okay, so basically a quick overview of recent quadrangle results. Okay, I am ready to take questions if any.
Thank you, Stan, for this extended review of relevant results. So please, if there are any questions from the from the audience, they are welcome.